Hello and welcome to the Minnesota Stormwater Seminar Series. My name is Jessy Carlson, and I'm very happy to introduce today's Stormwater Seminar speaker. This seminar series is funded through the University of Minnesota's Water Resources Center, the Clean Water Legacy Amendment, and the Clean Water Council of Minnesota, in partnership with the Minnesota Pollution Control Agency, and is hosted here at St. Anthony Falls Laboratory. Many thanks to Andy, John, and all the staff here at SAFL for hosting and leading the seminar today and for the past several years. For those of you online, please use the Q&A function within Zoom to post your questions for today's presentation and panel discussion. The title of this month's presentation is Performance and Maintenance of Sand Filters Amended to Retain Phosphate, and features the results of one of the many research projects supported by the Minnesota Stormwater Research Council. Today's presentation will be given by John Gulliver, Professor Emeritus in the Department of Civil, Environmental, and Geo-engineering here at the University of Minnesota and PI of the project. After a short break, we will then have a panel discussion featuring local water resource managers whose work is impacted by the results of the research discussed today. So please join me in welcoming John.
All right, can everybody hear me? Good. You can hear me online? All right. So, as Jessy said, thank you for that introduction. Jessy, I'm John Gulliver, Professor Emeritus in the Department of Civil, Environmental, and Geo-engineering. I do my research at the St. Anthony Falls Laboratory. And today we're going to be talking about performance and maintenance of sand filters amended to retain phosphate. We call them iron-enhanced sand filters. So it's a sand filter enhanced with iron to capture phosphate. So before I start, I need to start some acknowledgements. This is a project that was done for the Minnesota Stormwater Research Council. And there are lots of people that are involved in the project. The first two were Pete Weiss and Levi Burrows. They're the main people in the project. They first started by contacting operators because we need to get out and take some measurements. We need to find what sort of data is out there. These things have been around for 10, 15 years. No one has actually looked at them. And so our idea was to get out and figure out if they're working or not. They also did most of the field data. And then we also have some batch studies because we took the media and we tested the media. That means we grabbed the media from the filter, took it back to the lab and tested it. And that was done by Addie Johnson, Emma Squires, and Levi Burrows. And finally, review, advise, and handling research bureaucracy, which is a big part of it these days, was done by our research manager and leader now, Andy Erickson. Thank you very much, Andy, especially for research bureaucracy. So the agenda, we're going to start off with a purpose and history, have some questions about iron-enhanced sand filter. I'll talk about the questions that we've been hearing about iron-enhanced sand filters. We've been hearing them for a number of years, but it just took us a while to get this research going. Talk about the research objectives, and the main part of it is going to be methods and results. We have 3 methods to determine that we worked on for soluble reactive phosphorus, that would be basically phosphate. And then we also did something with regard to total phosphorus, because that's what the operators are interested in, is they want to remove total phosphorus. Although phosphate is seen by the MPCA as 5 times more biologically active than particulate phosphorus. So phosphate is a big problem, especially in Minnesota where we have so many lakes, and it is the limiting nutrient that stops your lake from becoming green and overcome with algae. And then we're going to talk about some operation and maintenance, some suggested operation maintenance for these iron-enhanced sand filters, and then I'll finish with the benefits of the research, which is kind of a recap, telling you what I just told you. So the purpose of the iron-enhanced sand filter, we started this work in 2003. Andy's master's thesis, actually, Andy Erickson's master's thesis was on this topic. And the idea was to develop a filter which filters particulates and also absorbs phosphate. And this is the result of a, oh, here we are. This is the result of a, oh, I don't know what's happening.
Hold on a second. There you go. Now try again.
Okay, thank you. This is the result of some column studies that Andy did back in 2003 to 2005. And you can see that we have influent phosphate concentration, 100% sand, 0.3% iron, 2% iron, and 5% iron. And this is the effluent that came out. Here's our influent, here's our effluent with 100% sand, 0.3% iron, 2% iron, and 5% iron. Really brought it down to about 10% of the total that came in. So that was a good sign. We decided that we would publish the results and wait for someone to come up with an application. So that research was done in 2003 and 2005. It was published by Erickson, Gulliver, and Weiss, Pete Weiss. And it took a while for it to get out there. The first installation was designed by Bar Engineering. They came over and talked to us, and they designed this, what I think is still the most beautiful iron-enhanced sand filter. This is it right here. And the idea behind an iron-enhanced sand filter, okay, I got it. The idea behind an iron-enhanced sand filter is that you let water run in, it goes through the iron-enhanced sand, that would be iron, a mixture of iron and sand, into a under drain and flow out through here. That's basically the idea. Now, a pond perimeter IESF was developed in 2010 by Ross Bittner, who was at the city of Prior Lake at the time. And the idea there is that you put it in at the edge of a pond. Here it is, the edge of this pond here. And so you put it in at the edge of the pond, and then the water goes through. The pond rises up when you have a rainstorm. The water goes through the iron-enhanced sand filter and out the underdrain. There's a third type of iron-enhanced sand filter that I don't have up here, but looks kind of like this right here. That's an iron-enhanced sand filter that is pumped. So you have your stormwater pond. You pump the water up into an iron-enhanced sand filter, and then it drains out. And that's useful when you don't have enough vertical drop, as many of these sites do. So, installations involving the iron-enhanced sand filter. Andy went down to Austin, Texas, because this is called the Austin sand filter, this picture right here. He looked at them and saw what they were and what they did. They generally are operated at a ratio of drainage area to sand filter of between 15 and 25 to 30. That's generally how they're operated. Sand filters were not that common in Minnesota at the time. And so people were really used to putting in sand filters. But in 2019, an MPCA survey indicated there were 171 installations in the USA, but the designs, construction, and maintenance were pretty variable. Everyone was trying something new. There was some guidance in the Minnesota Stormwater Manual. They wanted to improve the guidance. We worked with them to improve the guidance. But there were questions about the IESF that we could not answer. What maintenance is required? What's the maintenance frequency? That was a big question. How often do you have to maintain it? What's the reasonable lifetime of the media? How long does it last? And is the spent media toxic? I'll answer the last question right now. It's not toxic for metals because we measured metal content on all of the samples that we collected. And we collected a lot of samples, about 250 samples. 250 samples. We didn't find toxic metal concentration in any of them. Now, I can't say anything about organic chemicals like PFAS and all these other chemicals, but you know, they're first off, they're expensive to analyze, and secondly, they're everywhere. So I just took that as a given. Our objectives were to develop a convenient assessment metric, how to assess whether or not your iron-enhanced sand filter is working. And secondly, develop consistent maintenance guidelines. We want to reduce cost and maximize life. So, our research methods. This is what we put in our proposal to the MSRC. The first thing we want to do was to solicit and expand existing data. So we look for phosphate reduction and volume treated, because I thought volume treated might be a good metric for how the filter is doing. In other words, if you've treated more volume, then your filter probably has less capacity to remove phosphate. But there's volume treated in only 5 sites out of 100, and now it's about 200 sites in Minnesota. There are only 5 sites that had volume treating. Phosphate reduction on a few more, but we had difficulty obtaining useful data. Part B of our research proposal was to analyze existing data, including the QA/QC analysis. Well, the data was insufficient to really analyze, only 5 sites. How can you do a regression on data with 5 sites? And the 5 sites actually had quite a bit of variability in performance. So that was not successful. So we went to part C of our proposal, and that was, I don't know if I included part C. Oh yeah, that was to collect new data. So we collected phosphate, iron, total phosphorus, and flow on a number of sites. We ended up with about 22 sites. We monitored for PO4 reduction, so we had a monitoring device like you see right here. We have some monitors. We measured the PO4 reduction, but we needed to estimate the total cumulative volume of water treated, because that was what we're going to use in our metric. We also did media sampling. We took 5 samples at each iron-enhanced sand filter on the top, and 5 samples in the middle of the media, and determined total iron and phosphorus on a ICP OES, and we also did some batch studies to estimate the remaining capture capacity for phosphate. So that's item C. So those would be called method 1, method 2, and method 3. So method 1, measured performance versus water treated. The performance our idea is performance is proportional to the depth treated, not necessarily the water treated. And that would be depth treated would be volume treated over filter area. So you take volume over area, you get a depth. And so you can imagine that if you have a huge water column, that would be flowing through your filter. But we measured performance at a given time. And so for example, 2023, we measured this performance of this iron-enhanced sand filter. But then we need to know how much flow has gone through that iron-enhanced sand filter between the time it was constructed and 2023. So we need to develop a hydrologic model to do that. It took us a while to come to that resolution. So the first equation here is we used a very simple runoff volume model. Runoff volume is equal to coefficient, RV, runoff coefficient, times the area of the watershed, times the precipitation that falls on the watershed. We use this simple equation here for the runoff coefficient. Runoff coefficient is 0.05 plus 0.9 times the fraction of effective impervious area in the watershed. That's an adjustment of Schuler's simple method. Tom Schuler was here a while back giving a talk. It says he's basically known for this method. It's a very simple method. He used total impervious area because not many people know the effective impervious area. That means, what's effective impervious area? Basically, that means you don't count rooftops that are draining to grass. You just count what's draining straight to the storm sewer. So that's effective impervious area. And then these other two equations here, Ibrahimian et al., he was a student of mine that we developed previously. We use these two equations to end up with FEIA, our fraction of effective impervious area. So we took the data that existed on depth treated, measured depth, and analyzed it to see if we could use it for verification. So we have estimated depth up here, and for different years, you have estimated depth and measured depth, and then we have the ratio of measured depth over estimated depth. There is quite a bit of variation in this estimated over measured. You can see that it varies quite a bit, but if you come down here, you end up with an average estimate over measured of 1.14. I thought that was remarkable because first off, our model is not that good. And there's really no model that's that good. But secondly, there are also problems with measurements. You know, it's really difficult to measure flow, especially in a stormwater practice. One of the biggest problems in terms of measuring flow is that most people measure flow with an acoustic Doppler velocimeter. Now, acoustic Doppler velocimeter is inaccurate below 4 inches. So you got that much water coming out of whatever your treatment device is, and it's inaccurate. Your measurement is inaccurate. Below 2 inches, it doesn't work at all. You get 0. So we don't use, when we monitor things, we don't use acoustic Doppler velocimeter. The manufacturers will not say anything about that. And I think that's a sin. But anyway, that's what they do. That's just an aside. Don't use, so one side theme is, don't use acoustic Doppler velocimeter if you're trying to measure flow. Anyway, in a stormwater system, it's fine in a stream where you always have water, in a lake or something like that. Well, probably in a lake, but in a stream or whatever where you always have water, it's fine because you always have 4 inches of water. But in a stormwater system, you don't always have 4 inches of water. A lot of the water comes through when at less than 2 inches, and you are not measuring that at all. Okay, let's move on. So these are the results of performance versus depth treated. But there are some outliers here. Let me go through this. We have pumped IESFs, passive IESFs, and some outliers that were determined by the degree of uncertainty in the analysis. For example, if you had a media and if you have a site where you are measuring your retention of phosphate and it varies all over the place, well, that would give you a high degree of uncertainty. And so the standard deviation are the whiskers on here, and you can see that some of these are really big, like this one here. Well, we're calling that an outlier for that reason. The R squared isn't that high, 0.3, but that's the best we could do. There's a kind of a region where it goes from there's a region up here of sites where it goes from 0.85, kind of comes down. They're the better sites. I think that these are some of the sites that are less well maintained or not quite the right design. So if you are designing a new IESF, you can kind of get into the report and see what the sites at the top were versus what the sites at the bottom of this graph were. But overall, that's what we got. So media one will provide, method one will provide a justification for testing the media. Roughly 50% phosphate, soluble reactive phosphorus, retention occurs at approximately 12,000 feet of water treated. That's basically what we found. So method two, let's talk about method two. We tried lots of different things with this, so we want to provide tools to work with, to analyze your IESF, your iron enhanced sand filter. And we took the measured performance versus the capacity remaining. This is part of method two. And method two was we measured the total media, total phosphorus and total iron concentrations. So that would mean we send it out for an ICP analysis. That's the easiest thing to do. You sample your media, you send it to a laboratory, they do ICP analysis. It's kind of a standard method. They do it for metals, but in fact, they also give you phosphate, total phosphorus. And the total phosphorus is getting more and more accurate with these new ICPs. So you can measure total phosphorus, and that's what we did. So we plotted percent P retained, which we determined previously, that was also on the last graph, versus TP, total phosphorus, over total iron. The question is there a good correlation? And there wasn't a very good correlation, unfortunately, because we were looking at this as this is how to do it, you know. But the problem is that you can see our R squared is about 0.1, and there's not much variation in the iron to the phosphorus iron ratio. It only goes from about 8 to 4 for much of the data. So it really didn't spread itself out. And that's too bad, because that would be a great thing to do, just send it off. So method two was not that successful. Maybe it will become successful in the future when we get more data, I don't know. But it wasn't that successful in our analysis because there was not much variation in the total phosphorus to iron, total iron ratio. But there is a method three. Method three is we take the measured performance versus capacity remaining. We actually measure how much capacity the iron has. And the problem with the ICP analysis was that the iron is always there and the phosphate is always there. And that could be part of the problem. So this is more direct towards the retention of phosphate in an iron filter. So I was pretty sure that this would give a good correlation. So we have to determine the capacity to remain in the media. That's through batch tests. You can see these batch tests here. We ran a lot of batch tests. 10 batch tests, well, about 250 batch tests on all these. And so this is just part of the setup. I love watching these things shake and work and everything. That means you have an active laboratory. The capacity remaining, just a pretty simple equation. It's right here. The concentration, assumed concentration flowing in. You have to assume a concentration flowing in. You probably want to assume a concentration similar to the concentrations that really do flow in. But you can't have a variable concentration because that really doesn't tell you much, you know. And then you have a C sub F as a concentration at some time, at a given time. That's the concentration of P in the solution. So you run it on the shake tables for a while. You put in some water with some phosphate added to it. The phosphate is attracted to the iron in the media, and then you have less phosphate in the solution. You measure phosphate in the solution, and that would be C sub F. And the rest of this is our conversions, except for the fraction of iron in the media by weight. So that's what we do. We need to decide what our initial concentration is, And that's important for establishing the protocol, how to do it. So we're going to have a plot here I'm going to show you in a second. It's it goes with the protocol on how to do this. If you don't use the protocol, then you probably cannot use the plot. So they go together. And then we need to choose a time to determine CFs. And we did that by determining the best fit of the data. And here's some curves. These are actually pretty common. They look pretty much like this. We started with an initial concentration of 100 parts per billion, 100.1 milligrams per liter. And then took measurements at various times, 1 hour, 24 hours, 48 hours, 96 hours. And you can see that there is capacity, in this case, for this sample. You're going down to about 80% after 96 hours. We also did leaching studies, and that would be where you start at 0 and you come up to here, and then it ends up about the same, which is kind of a quality control aspect. It ends up about the same as the ones coming down with the concentration in them. These are surface samples starting at 0 and starting at 100 parts per billion. So these are the results. We chose CI to be 140 parts per billion. Even though the tests were run at 100 parts per billion, the endpoint is about the same regardless. If we started at 300 parts per billion, we were doing some early tests at 300 parts per billion, the endpoint was the same. So it doesn't really matter what you start at. After 96 hours, you're going to end up at the same place. So we chose 140 parts per billion because it made the graph a little bit nicer. We didn't have any negative capacity remaining. That was really it. So here's the capacity remaining at the bottom, from 0 to 0.06 in grams per kilogram. And this is the SRP retention that we determined previously, and we've been using that all along. That's what we've been using for the retention of the media. And this is the capacity remaining that we calculated based upon the batch tests. So here's the data. It has a high R squared, 0.88, and it has a pretty good spread down here. There are some outliers. Again, the outliers were determined by a high uncertainty in the media. You can see this one here has a high standard deviation. This one has a high standard deviation. And this one has a high standard deviation in terms of the capacity remaining. So that's method 3 results. So method 3 was successful. It provides a means of testing media for soluble reactive phosphorus reduction, but it's not a standard test for any analytical laboratories, unfortunately. So we have put the protocol for the test to use to use figure 3 in the report, method 3 in the report. Now, people are really interested in total phosphorus retention for the most part. For total phosphorus retention, a sand filter is designed to retain particulates. And we have data out there on that. There's data in the International BMP database on sand filters, how well they remove total phosphorus. But we thought we'd give this to you anyway. So here's how the iron-enhanced sand filters work with regard to total phosphorus retention. We did the same thing we did for phosphate. That is, we have TP retention that we measured versus depth treated. That's the depth treated, volume treated divided by the area of the filter. And we got this plot. It looks pretty similar to what we had for SRP retention. Actually, it's very similar. So that means that your total phosphorus retention is about your phosphate retention. What does that mean? Well, I thought about this. It took me a while to get my head around this. What's happening is that you're pulling out particulates, and the particulates are there in the media. Well, they're going to degrade, right? They're degrading over time because they're organic material. And eventually they're going to release that phosphate. They're going to release phosphorus as phosphate. And so when you're capturing these things, when you're capturing particulates, eventually, if you leave it there long enough, you'll be releasing phosphate. So that's something that comes with the territory. You're capturing stuff, and the capturing stuff degrades, it releases something. So even to remove particulate phosphorus, a sand filter cannot last forever. But anyway, this is a figure that can be used. We also developed this plot here and this equation for modeled TP retention. We took the measured percent TP retention again, and we plotted against, and we took a model, and the model is 59.4 times the area of the filter divided by the total impervious area, now instead of effective impervious area, times the age of the filter at the bottom, divided by 10 years. That's what we use as our way to make this equation non-dimensional, because this is a multi-parameter equation. So you have to have it non-dimensional. Well, you don't have to, but you should. So our age, 0 is 10 years. Age is the age of the IESF. TIA is total impervious area, and AF is area of the filter. Why did we use total impervious area? Well, we tried effective impervious area, and it was not better. It was about the same. So we figured we'd just use total impervious area. So that equation, you can see it. You can kind of get a curve out of it. And there are some examples of using this formula. Here is the formula turned around so that age is on the left-hand side. You want to know if you're developing, building iron enhanced sand filter, you want to know how long it's going to last? This might help you. You choose your percent retention, your final percent retention. And if you choose, for example, 40%, and you have a total impervious area over filter area of 15, then your age would be 42 years. It would last 42 years. After 42 years, it'd be at 40% total phosphorus retention. If, however, and we had many sites like this, your total impervious area over your filter area was 1,000, not 15, but 1,000. And your final retention at the point at which you reach 40% then is 10 years. So that's why some of these filters are not lasting as long as others, because the total impervious area over the area of the filter is a lot larger. They're running more volume through the filter. Of course, it's not going to last as long when you got all that volume going through the filter. I'm answering a question many people have asked me, because I think someplace it says they'll last 35 years. And I think that I'll explain it a little bit. Let me see if I have some time. I'll explain it a little bit. Andy, Pete, and I put an analysis in the paper where we had assumed a certain amount of ratio, and that ratio gave us 35 years for the filter to last. But that was based upon the ratio we assumed. And we made the mistake of putting 35 years in the paper. So everyone picked up the 35 years and didn't think about the ratio. Okay. I forgot what the ratio was. Do you remember, Andy? I think it was about 15 to 1. Yeah. So The last thing we did was we suggested some operation and maintenance for IESF performance because we were out looking at all these things. We wanted to feel that we looked at about 30 of them total. We didn't analyze all of them, but we looked at them and we wanted to come up with some improved suggestions or for operation and maintenance. And number one is to let the professionals mix the sand and the iron. Let Playstead mix the sand and the iron. They do it. They're professionals at it. If you get out with a rotor tiller and try and mix the sand and the iron, I can tell you almost, if I got out there with a rotor tiller, I would think it's mixed and it's not mixed. I would say, oh, it looks really mixed. It's not mixed. I can tell you that right now. If you go twice as long as you do twice as many passes as it takes after it starts getting mixed, it's not mixed. And so you really need to let the professionals, the people who do this all the time, mix the iron and the sand. Another way of handling this would be in year one, inspect your IESF after every large storm. So that can set up an O&M protocol that will last for the rest of the IESF's life. So if you have a 1-inch or a 2-inch storm, go out and check it out. Just drive by, stop, take a look. What's it look like? Number 3 is keep the surface clean. That means raking off any decaying material. And I thought about it, and we decided that pulling plants in the late summer, early fall is a good idea. Why? Because those plants are going to die. They become organic material that is degrading. And with, guess what in it? Phosphate. So it really hurts your goal to let the plants grow and degrade on the top of your IESF. 4, exposure to air. And we knew this. Oxygen is important. Both the bottom and the surface need to be exposed. And people have been doing this. That's why we have the pumped IESFs, because they couldn't otherwise make sure the drain tile would be free of water most of the time. But I'd like to carry this a little bit farther to say extended flooding should be avoided. If it's flooded for a week, that's not a good idea, because your phosphate will start to come off of your iron. Your ferric iron, iron plus 3, becomes ferrous iron when you have zero dissolved oxygen. And so you slowly move to the zero dissolved oxygen. It takes about 5 days, or sometimes longer, but 5 days is a pretty good number. After 5 days, you have ferrous iron because you have zero dissolved oxygen. That ferrous iron releases the phosphate, and so basically you're supplying all the phosphate that you have captured, you're supplying that to your water body. So extended flooding should be avoided. That's important to remember. So the benefits of the research, well, we have 2 methods of determining performance of an IESF, iron enhanced sand filter to retain phosphate. We have this equation here, which is depth treated versus SRP retention. Here we also have SRP retention versus capacity remaining. Here you're just doing a paper analysis, a desktop analysis on data that you already have. Down here you are sampling the media and determining how much phosphate retention capacity is left in the media. Says the same thing. We also have an equation to estimate total phosphorus retention with this equation down here at the bottom. And we have research-enabled improved O&M suggestions, which hopefully we'll be able to get into the Minnesota Stormwater Manual. So thank you for listening. I'm done.
Thank you, John. We've got about 10 minutes for questions. And we'll take questions from the audience as well as from online.
Hi, John. Thanks. So back in my PCA days 1,000 years ago, if I remember correctly, we gave flat credits for iron and just a single number. Based on your research, it looks like that maybe, because permittees care about crediting, that you could start to refine those credits and base them on some of the equations and the factors that you had. In other words, you wouldn't have a static credit anymore. It would be based on some of the information that you've got here. Does that sound correct, maybe?
Yeah, that is correct. We can adjust if the MPCA wants to. We can adjust it. It gets pretty complicated if you go all the way to using the equations that we have, but that is possible. The credits could be adjusted. I'm not sure that everyone wants to have the credits adjusted, but.
Do we have any questions online? All right, we'll take one from online.
Our first online question is, what is the chemistry at work which makes the iron-amended sand filters work to remove phosphorus?
Well, yeah, it is adsorption with a chemical attraction to it. You have iron, which is a +3, and phosphate, which is either a -2 or a -3. And the iron is either a +3 or +2. And so when they get attracted, when they come together, they form a solid. That's basically it. Adsorption with chemical enhancement.
Paula?
Apologies if I missed this, but you spoke about results in terms of the depth of water treated, but did all of these filters have pretty similar depth of media? Because, and then we also talked, yeah, so.
You didn't miss anything.
Okay.
Yeah, most of them had the similar depth of media. And that would be about 18 inches, 1.5 feet. But that was a good question, actually.
Thanks, John, for your work on this. My question is in regards to your point about pulling and harvesting the plants in late summer or fall before they decompose and release dissolved phosphorus. My question is, would it be a better strategy to avoid plant growth and try to keep these media filters clear of plants to not have to worry about that, or to encourage plant growth and strategically harvest them before they decompose, as those plants might pull the dissolved phosphorus out of the media?
Yeah, that's it. Good question. Plants and phosphorus retention don't go together. So if your media, and this is based upon a study that Andy Erickson did outside, if your media is pulling phosphate out of the water and it's not giving it up, then the plants aren't going to grow because they don't have any phosphate. They need phosphate just like the algae do. So if you want to retain phosphate and do a good job of it, you're not going to be able to grow plants. There are some that can grow at very low phosphate levels, and they'll be kind of like low-level plants, and they'll be sparse in the area. You want to pull those, and you don't want to try and grow plants. First off, it's difficult to try and grow plants. If you can grow plants in your IESF, in your iron enhanced sand filter, then it's probably not working the way you think it is. So you want to, but you do want to pull the little scrubby plants that kind of grow spread out over your filter, because they will degrade and they will basically release their phosphate.
Why don't we take a question from our online audience?
Do you think the differences in treatment by the IESFs could be in part due to differing filter porosities affecting how fast influent is flowing through and being treated, not just the treatment depth of the IESFs?
Yeah, I think there is some of that. Most of them are similarly designed in terms of the media. They have a certain media, which would be C33 sand, and the iron particles are the iron particles that we have told people that they need, and that'd be about the same size as a media. So I think that most of them have a pretty quick flow-through speed. But there are filters that have a slow flow-through speed because they have a filter fabric on them, and they are well performing. And they haven't had any clogging, and they're well performing. So one thing a person could do is think about designing their iron enhanced sand filter to slow down the flow through the filter. But we only found one filter that was like that.
John, on your total impervious area, I was just kind of curious, like how much, if you're saying you're not taking roofs, like what percentage that is, because from experience more about consumption of groundwater, we looked at when I was in Prior Lake and now in Comfort Lake, Forest Lake, doing infiltrometer tests and new construction. A lot of it's backbladed, and when we did those tests, it was not far off from just hard impervious surface. They needed constant groundwater consumption to keep it green. So if you're having a flush from a roof and there's fertilizer, you may actually be increasing the flow off that lawn. So I'm just wondering how much factor that is in certain areas from a calculation standpoint.
Yeah, in a really high precipitation event, you will have flow off the lawn. And it depends upon what sort of infiltration you have in your lawn, right? For the grass to grow, you have to have at least that much really good arable, at least 6 inches of arable subsoil, arable soil. And that'll be pretty porous. So if you take 6 inches and take 40% of that, you're talking 2-inch rains, really, maybe 1.5-inch rains, at least, that your lawn can absorb. But beyond that, your lawn, this is my personal opinion, I could be wrong about this, but beyond that, your lawn is not going to absorb the rain. And it probably won't absorb it if it's coming down too quickly because of your infiltration rates at the surface. So, yeah, I think that could be a problem, but I don't think that's a huge problem, unless you're right next to a lake.
Well, it was water that's like subsurface was backdated, just hard, and then the turf just made on top of it. So there is no ordinance required off the
Yeah.
just like talking out of line.
Okay, yeah. The question is, you have a hard pack, and you have some surface material put on top to grow plants. Your trees don't grow very well either, do they? Yeah. Can't get through that. Yeah, that's a problem. And where that exists, then you want to be careful with that.
Let's take a question online.
Yeah. What are the professionals doing to mix the iron and sand that maintenance staff can't do with a rototiller or other mixing equipment? And is there analysis that needs to be done during the mixing process to ensure proper mixing?
Well, they basically take 2 streams and they flow them into a hopper. And I've never actually seen this is done. I just my thought is this is how it's done. They flow them into a hopper, and so they know they have a good distribution between the two. Has anyone seen this been done? What they do? Okay, maybe you can tell us.
Yeah, you have, companies out there that deal with, or material handling companies. I don't want to necessarily name drop anybody here, but they can do it off-site, they can do it on-site. I was involved in an iron sand filter installation in Blaine that they mixed it on-site, and they brought out a portable mixer, just specialized piece of equipment to do the work. Worked great, and I believe the filter is still working great today.
Is there issues with the settling of the iron if they do it offsite and then transport it?
I've heard of that being a concern. I don't know if it's actually been shown to be a concern in installation.
Randy, do you have a question?
Who would have thought? Thanks for all the work, John. In this study or others, do you have information about the cost efficiency of iron-enhanced sand filters? You know, in terms of the cost per pound of phosphorus removed, how does it compare to other types of practices? And one of the striking things is it seems like a terrific idea that just hasn't been implemented very much. And does the cost efficiency justify much broader implementation in your view?
Well, my answer to that, we don't really have haven't done some really good analysis of cost efficiency, but an iron-enhanced sand filter is not going after the low-hanging fruit. So you need to get rid of everything else. Through settling, that's really the easiest way of doing it. A pond works really well to remove your phosphate because basically you're growing algae in the pond and hopefully settling those algae out. And then so you have less phosphate leaving the pond than coming in, hopefully, if it's operating properly. So filtration is it's a way to remove things that you cannot remove through other means. So if you still have to get the phosphate out of it, then you want to put in something like an iron-enhanced sand filter. It is not the most cost-effective per pound of phosphorus, however. It's getting at really hard phosphate to remove.
Do we have another online question?
Does this research apply only to surface-based sand filters as opposed to subsurface sand filters like those that are contained within a cell of a concrete vault?
That's a good question. It would apply to all of them. The subsurface sand filters are not always, but very often proprietary, and so they have their own method of dealing with these things. So it would apply to a subsurface sand filter as well.
Do you think there would need to be any additional considerations in a high concentration environment such as rural or agricultural areas?
That's interesting. We haven't done that much agricultural research. We're typically doing urban research. But if you have a high concentration coming in of phosphate, if it's not phosphate, if it's particulate phosphorus, then you can filter it and just clean your filter, right? Or you can settle it, which would be better, actually. It's probably most cost-effective to settle it as best you can. But if you have a high phosphate concentration, then everything would be different. It would have, because you have less time before you have before your media is no longer able to absorb the phosphate. Yeah, that's true.
We did actually have one site where we tried an agricultural iron-enhanced sand filter. It got used up very quickly because the drainage area to the treatment area was very large, very small filter for a very large drainage area. And it did have relatively high phosphate concentration. So if we were looking at our curves and our data, it was one that got used up very quickly. We only have one instance of that.
Anything from our online audience?
We do have another online question. We have a question for clarification about method 3, capacity remaining grams per kilogram. Is that kilograms mass of the initial iron or the iron sand mixture?
Oh, that would be per, I'm not sure. I think it was kilograms of initial iron. Yeah, it was grams of iron because we had the percentage in the equation, we had the percentage of iron by weight in there. So it was kilograms of iron.
Another online question, if you would like. What constitutes a large storm regarding the year one inspections?
That's a good question. And I thought about that. I thought about, a large storm would be one that would cause the pond to increase in level and flow over your iron and hand sand. This would be for pond perimeter trenches. So I guess that would be what I call a large storm, when your ponds are increasing in level and flowing over your iron and hand sand, so that the duckweed and the water meal cover the surface of your iron and hand sand. You want to get out and see what happened.
All right, well, that'll be it. We've got 5 minutes for a little bit of a break, and then we will regroup back here for our panel discussion at 11 a.m. Thank you, John.
Okay, thank you. Thank you.
Welcome back to the Minnesota Stormwater Seminar Series.
That's a nice presentation.
I'll be moderating the panel discussion. I'd like to remind everyone in the audience that this discussion will largely consist of your questions. If you are joining us online, please again use the Zoom Q&A function to ask your question or to upvote questions that have already been submitted. For those of you in the room today, we'll be passing the microphone to take questions. So to get us started, I'd like to introduce our panel and offer a first question. On my right, your left, our first panelist is Paul Strong, who is a water resource project manager at Bolton and Menk. Paul, from your perspective and experience, how do you relate to this topic?
Well, it's great to be here. As far as iron enhanced sand filters go, there's really two avenues that I approach IESF as part of our work. One is from a site design perspective, specifically trying to meet some treatment goal for watershed or state permitting requirements, or from the city perspective, trying to meet some sort of waste load allocation requirement. So if you've got a TMDL or some other phosphorus reduction requirement as part of your city stormwater management program, we use IESF for that perspective as well to try and meet treatment targets.
Great, thank you, Paul. Our next panelist is Bridget Osborn, who is the Water Resources Group Manager at HR Green. Bridget, from your perspective and experience, how do you relate to this topic?
Thanks, Jesse. Hi, everyone. I'm similar to Paul. So I've been working with all stormwater for 15 years. And yeah, iron enhanced sand filters definitely come up when you have that hard to treat total phosphorus requirement on multiple projects or just waste load allocations. So yeah, looking forward to this discussion on everything.
Great, thank you, Bridget. And next up, we have Chris Kucek, who is the Facilities Operations Specialist at Capital Region Watershed District. Chris, from your perspective and experience, how do you relate to this topic?
Thanks. So at Capital Region Watershed District, we've got a number of capital projects that have involved iron enhanced sand filters. And so part of my role is to oversee the maintenance of them. So from a practitioner standpoint, it's been sometimes a challenge to figure out exactly how we're supposed to maintain them. What does a working one look like? And then also ours have always been involved in retrofits. So kind of fitting in the iron enhanced sand component into a pre-existing pond has been an ongoing challenge for us.
Great, thank you. And last but not least, we've got Ryan Johnson, Environmental Manager for the City of Roseville. So Ryan, how do you relate to this topic?
Thank you, Jesse. Thanks for having me here. Roseville's a first-tier suburb and first-ring suburb, and everything we do is fully retrofit. We have very few projects where we're actually going in and just doing a new BMP, especially on with iron enhanced sand. So a lot of it is trying to improve, our waters, trying to reduce our waste load allocations, things like that. And yeah, a lot of it is just trying to get into our existing features, trying to make them function a little bit better. And then as the practitioner side of it, how do we do this? And then also, how do we maintain it long term? Nothing, my streets guys who do a lot of the maintenance, they're fascinating people. They definitely tell me what they think when I ask them to do some of these little bit more prescriptive items on, especially like the iron and hand side. So everything from the design, install, and maintenance is, what we're doing in the city. So I think the research that John and St. Anthony Falls is doing is fantastic. And yeah, I think we'll learn a lot today.
Great. So those are our panelists today. We can open it up to the audience, both here and online.
With hopefully the increased emphasis on street sweeping to target dissolved phosphorus, how do you see iron enhanced systems fitting in, and where do they fit into the stormwater treatment system?
Well, I'll go. All right. Yeah, within Roseville, again, it's like we do street sweeping to target because we want to get everything we can off the street first. It's the cheapest, it's the easiest. And then, we can also test what's coming off the street, so we can grab data like that. The iron enhanced component of that is, again, just one more tool in the toolbox that, if we need to target, for example, Lake McCarran's, where we've done iron enhanced projects, we know that it is, we have a high canopy, we have a lot of leaf litter. The drainage area going to McCarran's is massive. We have very few areas that treat a lot of the stormwater. So once we kind of combine street sweeping to get that first, get that gunk and some of that first flush off, the iron enhanced, is we're really targeting a lot of that, basically that phosphate that's going into at least William Street at this point, before it gets into McCarran's. So it's just one more piece that we're doing to try to protect the lake. And then, downstream, it goes through Trout Brook and into the Mississippi. So it's just one more piece that we use. And, a lot of them are built in right now, at least, so they can function long term. And we do a fair amount of just maintenance monitoring every year just to make sure that everything is working like on the city level.
Yeah, I agree with pretty much everything you're saying. It's just one more tool to try and optimize city resources and tax dollars to achieve some kind of objective, achieve either higher water quality in a lake, protect some downwater water body. Iron enhanced sand filters can be a very useful tool for that, but it's trying to find the balance of what lower hanging fruit can we achieve first using simpler maintenance, simpler BMPs that have easier maintenance requirements or longer design lifespans, but still looking to IESF for retrofits in tighter areas or in areas of special concern, like a trout stream.
I'd just say that, yeah, if we can squeak out a few more years by picking up more leaf litter on the curb before having to maintain the filter at the pond, then that's, it still makes sense to put it in during a retrofit, and maybe we can do some other upstream practices to try to extend the life of it before needing to change out that filter.
I don't know what else to add, so.
Do we have any questions from our online audience?
Sure, we have a question here that it's a little bit specific to John, but I'm going to open it up a little bit to everyone else as well. Someone wants to know, could the ratios and equations be applied to other enhancements like alum-based drinking water treatment residuals, or would separate analysis be needed to develop ratios specific to different enhancements? But personally, I'm also curious, what is the level of interest and what do you think is the degree of potential for using these kind of alternative materials? Do you think that would be something that's beneficial to the industry, or is it more of chasing an idea of, well, we could do this, but is it practical?
Well, I guess I should start. I think you would have to redo the research, maybe if you want to go with alum-based water treatment residuals. you would have to redo everything, I think. Because we don't know, I never worked with alum-based water treatment residuals, but there are certain aspects of it that would require, some investigation. I would like to say, however, that that filters, any sort of filter, especially any sort of filter, is really not the most efficient way to remove phosphate. Am I answering a question they asked? I don't know. And so if you go with a sand filter, just sand, you're going to have to do a lot of maintenance. If you go with an iron-enhanced sand filter, your maintenance is a little bit more difficult, but not that much. A few more things to look at. The same is true of water treatment residuals. They're in a filter mixed in with a sand filter. And so these filters just require a lot of maintenance. Unless you come in with a replacement module, like the commercial filters that have to be replaced more often, which is expensive but easier on maintenance staff.
Yeah, I'll follow up on that. For industry and just city designers in general, we would be interested in more materials. I'm hearing more and more about manufactured treatment devices with the proprietary cartridge filters or some other mix for particularly built-up environments. It's a fairly niche application though, but if there is some alum version of an iron-enhanced sand filter that could work, there'd be interest, but we definitely need the research to support putting any kind of installation with a different media mix.
Maybe I'll add a little bit just on the maintenance side. I mean, yeah, you're right. Every filter is going to require maintenance. Every manufactured device is going to require maintenance. You really just need to talk to whoever's maintaining these things and see what resources they have and what their preferences are. And obviously maintenance crews are going to change over the years, but I mean, really, I think that's the source of the decision making sometimes, so.
I'd be interested in it, but I feel like I have enough questions on iron enhanced sand that like a brand new filter, I just, it'd be cool, but yeah, it would take a lot more research before it was ready for like implementation wide scale.
All right. I'm fascinated by it, so I'm going to say yes. I would sign up for pretty much any other media that comes out. So anybody has ideas, come to Roseville. Looking at you, Andy, up there, and Dr. Gulliver. No, so it's like Roseville has one spent lime filter within the city too. Most of ours are iron enhanced. We do have cartridges and things like that. But yeah, it's like we have one other spent lime as kind of a trial, and again, it's like it's one more tool that we can go to. It's having the options on what can be installed to remove phosphorus again is what we're looking for. Yeah, I can't speak to the math and the equations, and that's why I look to the doctor to my left here on things to do with that. But yeah, from my side of things, it's like if we have more options, maybe we get better pricing to install it. Maintenance, again, is always going to be an issue no matter what. There's always going to be the specifics that, whether it's we hire it out or we do it internal, there's always going to be pieces that we have to do. And honestly, it's like with a lot of our projects that go in, if we have a spent lime filter and the spent lime's not working, it's like I can get mad enough at it to rip the spent lime out and I can put iron enhanced in. So once the infrastructure is there, that's my big component. So if the media changes, I can change media. And it's like we have the stormwater budget to kind of handle those types of things. Do I want to? No. But, if it helps, again, kind of move this research forward, get some other projects in the ground that, we can all look at and learn from, we have opportunities. So I'm always for it.
We have a project funded by the Minnesota Stormwater Research Council, the wonderful Minnesota Stormwater Research Council, on finding these types of treatment and types of media that can remove phosphate. We're concentrating on phosphate and be cost effective. So we're looking at a lot of things. In about 3 years, we'll have an answer.
All right, I'll be there in 3 years.
Okay, good. So do I, hopefully.
I was really interested, Dr. Gulliver, in the research around how many years a particular system would last and how to estimate that. And I could see the factor you're using is primarily the total area of the surface area versus the surface area of the system. I'm curious, as we see extreme precipitation events getting more intense and more frequent, do you think there would be interest in research around trying to hone that down a little bit to figure out, instead of estimating years, could you figure out how many storms over a certain size could a particular system manage? And of course, factoring in the total surface area. So one question is, do you think that seems like something folks could start to look at? And also, would that be useful to folks in the field in terms of maintenance, having a little bit more, a finer tune on that so that you could know when it's time to switch out or rotate some of the media or whatever makes most sense?
Yeah, I think that what you say is true. We have a non-stationary climate, and so the year analysis is really good in the present tense, probably not the future. There's one aspect of that, though. If you're talking extreme storms, which are probably going to have the greatest increase in extreme storms over, minor storms. An extreme storm bypasses a filter anyway, a storm filter, because it's just not frequent enough to treat. And also that is why we started with depth treated. Depth treated would be the same regardless of, it'd be the same parameter regardless over time. So that's my answer.
Anything else from the rest of our panel before we move on? No? Anything from online?
I've seen a couple of questions here asking about IESFs in a rural setting. It seems that the general consensus in the room is that an IESF is kind of like a targeted intervention that's best deployed in a specific situation that calls for extreme phosphate removal. But yeah, does anyone have any thoughts on the deployment of IESFs in an urban environment versus a rural environment?
I'll start. For an urban environment, it's often the only option to meet a specific treatment goal beyond going to, say, a manufactured treatment device or some other kind of proprietary device, which is why they're more often used in developed areas. For rural areas, usually comes down to cost. You have access to land, it's usually cheaper and more easily programmed into a maintenance budget to just have a larger alternative kind of feature, a traditional wet pond or a typical sand filter, some bioretention potentially. So iron-enhanced sand features aren't commonly deployed in rural areas because they just don't make sense on a cost basis.
And I guess I'd say, yeah, it's more for targeted use. So if you do have a basin or a pond or a lake or anything that has that total phosphorus, increased total phosphorus amount, that you're trying to get rid of, yeah, then if it's targeted and you want to do the iron-enhanced sand, we've done some in rural areas. So yeah, I think it does make sense on a targeted application.
All of ours are within a very highly developed area, and so land is at a premium. So if you've got space and, as was mentioned, like a specific target, especially for dissolved phosphorus or bioavailable phosphorus, that seems like it would be kind of nice, actually, to have the room to put in an appropriately sized one that could go for the length of time, a 30-year window rather than 5 or 10 before it gets filled up. We're those ones that are too small that were mentioned.
Yeah, Roseville. I've been in Ramsey and Roseville for my entire career, so not a lot of agriculture in my history. So But I do, it's like I always kind of wonder how it would be to like be able to size a BMP effectively, instead of just taking the little spot that I have and then putting something in there. Hence why we do go to a lot of the effective, treatments too, to kind of make it a little bit better. So, yeah, a little too urban, but hey, I would agree with the two on the end that are talking about developing elsewhere.
Of our experience in, I think it was, rural county, is that the concentrations of phosphate and total phosphorus coming off these agricultural lands, especially lands that have grazing on them, they are tremendous. And so the lakes are just really getting beaten up by this. So I think that people need to look at that, to look at their lake and think, well, what can we do to improve this lake? An iron enhanced sand filter would not be the first thing to investigate, though.
Yeah, I guess building off this discussion, my question is, I think we all understand what an optimal IESF design is, where we have that small watershed to surface area ratio, we have enough vertical head to completely dry out and not have tailwater impacts, we have 15 plus inches of media depth, et cetera. But it sounds like a lot of you have experienced more with retrofits and fitting things into small places. And I guess the question is, what lessons have you learned implementing these suboptimal designs, things that you wouldn't repeat again? Or on the other hand, what positive experience, things that you, like, they're surprisingly working well?
I guess we got a trend. I'll start. For a BMP that's sized to fit the site that it's on rather than the drainage area going to it, the best example I could think of would be an IESF in the city of Forest Lake by City Hall. It's along a judicial ditch, and that particular filter is a coupled wet sedimentation basin with a lot of vegetation around the edges and then an iron enhanced sand bench. That's been a very positive experience for the city in that it has had noted improvements in downstream water quality. Maintenance has been a challenge, but coupling it with some relatively oversized pre-treatment device, the wet pond upstream, has at least in our observation, extended the life of that basin, even though it isn't quite right-sized, especially given the recent research, for its inflowing drainage area. Given its location in a very visible area as well, there's an educational plaque. It's been good for public outreach and maintenance staff education, what's it supposed to look like, and how is it supposed to function as part of the city's overall treatment program.
So I guess with maintenance and everything, it would be nice to take, if you're designing an IESF for any one retrofit, it'd be nice to take their maintenance staff to someone else's IESF to say, okay, here's what they do for maintenance, here's what you can expect. There's some that we've done where, they're not getting the water that we were hoping for. So the basin that it's attached to just doesn't get high enough to spill over onto the IESF. So again, more drainage area kind of things to look at. But yeah, looking at, complications for maintenance, maybe lack of maintenance, just having that understanding of maintenance. I think those are some of the lessons I've learned.
The most recent capital project that we put in with an IESF was on Como Golf Course, one of the ponds on the golf course. And for the outlet control structure, we included a programmable valve, so we can sort of adjust how long, based on the storm, we can adjust the level and let it out at intervals or at a certain duration. So that's been nice. One of the questions we've had is how long is too long? How long is inundated? And if we could leave it longer and let more of it go through the filter, that would be great, but we also don't want it to go anoxic. And so having that flexibility, we can still change the kind of how it flows tomorrow, rather than just like a set, this is the overflow elevation, and after that, you're kind of not getting treatment past that elevation. So that's been, we've used those Opti RTC valves for other practices, but this is the first one we used it for a bench like that, and I think it's been a good idea.
For Roseville, most most of ours have been working really well since we've installed them. We did a lot with a lot of our watershed districts, so we had a lot of good partners with it that helped with design. The one that I've learned probably the most from is we have off of Oasis Pond, which is just north of like Rosedale and everything. We have 2 filters, which basically we pump water out of Oasis. We let it filter through these basins. And, when it first started, basically it was like, just thinking for the maintenance part of it, when these are going, it's like, usually we go out and we check our pond, any of them that have the filter bench around them, after the big storms, things like that. So that's how we kind of think. But also now you have this pumped system, which is going into these basins. And then we would get complaints that water is like running over the trail. And it's like, was water running over the trail? So you go and look at it, and the amount of water that we're pumping through this, it's time to make sure that it dries down, it dries out, we don't go anoxic. But it does create a nice, film on the top that if we don't go out and do enough maintenance, which was just go out and just rototill it. So we actually increased that. So now it's like that water always has someplace to go. So that was, just one thing that we found out pretty quick was, just in our ones that we're constantly pumping on, because it has that much more water going, because we're not relying just on rainfall to bounce the pond up. It's like we're actively pumping. So those ones just required, it's kind of common sense, put more water over it, you have to maintain it more, but it did take me a while to figure that one out. So, but now that it's operating, we have a nice maintenance schedule for it, and it's working like it should.
So one thing that we noticed when we sampled the media is that at some sites, the media would vary in terms of how much retention capacity it had tremendously. At some points, it had virtually 0 retention capacity. At other points, it was virtually like new media. And I think that's based upon distribution of the water. So if you're designing or maintaining a iron enhanced sand filter, you want to think about how the water is going to come onto the surface of the filter, and where the filter is going to take more water and where it's going to take less water, and possibly adjust your surface level for that. And make sure that you have it perfectly level, but you don't have low points, because that's where the water is going to go.
Got one more question here in the room.
Thank you. Just a follow up to that, were you able to take multiple samples at a certain site to kind of confirm that it was different throughout the filter regarding like where water is going? And it's
Yeah, well, we took 10 samples at each site, and so it'd be 5 across the surface and 5 in the middle of the sample, and so it was apparent when that happened.
Let's take an online question.
Sure. Continuing with the maintenance theme, we have a question here asking, does anyone have experience with biofilm accumulation on the filter bed and their impact on infiltration rates? Any recommendations for removal of biofilm and vegetation over a large area, about 2/3 of an acre? Hand pulling is a lengthy process.
I guess for Roseville, it's like we don't have anything that size, but I know we do have we have one large basin that's all iron enhanced sand, captures runoff from residential neighborhood, and for what we've been doing, it's like we've just been tilling it in. It's pretty sparse. We do have a nice mix of iron enhanced sand in there, so it's not like it's vegetated from side to side. And so, yeah, it's like we've had good luck with tilling it. We've also had maintenance rake it off, because I think the overall size is like 8,000 square feet or something. So if they wanted to go through, they could rake it. They could remove any of the taller stuff or any of the weeds too. But yeah, for the most part, it's like we've just been tilling it, given that's most effective for us. And it's not 2/3 of an acre.
We've done a mix of tilling and just like weed whip, and then followed up by raking it off. And I think it's been roughly the same amount of work. I was sort of concerned about tilling in more organic matter and kind of hastening that degradation process. So I was trying to figure out a way without having to hand pull, because it's several thousand square feet. I think it'd probably be more labor than the folks are willing to do, trying to find some happy medium where we're getting as much organic matter off the filter as we can without creating too much hand labor. None of ours are like tractor or like driving equipment sized, but that's something that if there was access, maybe you could drag behind some sort of rake and speed it up a little bit from just handwork.
All the ones I've worked on or currently work on maintaining are pretty small, so hand pulling's been good enough. But yeah, if you've got a large enough site, some kind of mower, track vehicle, something just so you're not compacting the media or damaging the drain tile would probably be the way to go.
I'll just add on to, for anyone putting in drain tile cleanouts in their filters, to have them marked very clearly for any rototiller operators. Had the same one hit twice, and it's not easy to fix.
This question is for Dr. Gulliver. During your presentation, you mentioned the use of a filter fabric. Can you explain how that was used? Was it around a drain tile or was it beneath the media?
Yeah, we found one site that had filter fabric. It was performing better than the other sites, and that was in Capital Region's Watershed District. So maybe you should answer that question. I think that was the William Street site.
Oh, that's a Ryan question then.
It's in Roseville.
Yeah, it's both.
It's both of us. So.
Okay, all right. So that's okay.
All right. So no. So yeah, that one was put in 2011. That was our oldest BMP that has iron enhanced sand in it. Yeah, basically it was just the wrap was put around all the media, so bottom, and then came up the side. So it's like all the iron enhanced media is in it. So it's essentially a little burrito with the drain tile down the middle of it.
Why hasn't that clogged?
I do a fantastic job at maintenance.
I think need more maintenance then, huh?
Roseville does a fantastic job.
All right. How about a question from online?
Yeah. Are there any design elements that tend to cause the most headaches for operations and maintenance? And what should we as designers avoid? Or conversely, what design elements have been the most helpful for long-term maintenance operation?
I'm gonna jump in. I've heard, so with the rototilling of the clean out comment, it made me think of putting your clean outs above the overflow elevation. So if your pond or filter is clogged, you actually have access to your clean outs. So that was one big thing, I guess. I'll jump in quick.
Something I was just thinking of during the presentation was we've got a lot of like native plantings surrounding the ponds as part of the restoration or retrofit work, but like equipment access and like having some sort of path that's not going to get wrecked. It's not going to wreck the expensive landscaping surrounding a pond when maintenance needs to happen would be like a useful thing to think about at the time of design.
Yeah, maintenance access is our biggest complaint. We obviously want all this to work. We want it to last long term. And yeah, it's like trying to find the balance of we want to have something restored around the outside of it, but then we still need to be able to get into it. So that's always kind of the biggest hurdle because, you want to optimize the size of the BMP, which usually, again, kind of in Roseville's case, you have to start tightening something else up. So all of a sudden you don't have a berm that maybe is wide enough for you to drive, even a pickup down. So it's the maintenance and just kind of the design of it on the front end has to be included. So, because yeah, it's like you can go through and you can, wheel a rototiller or something down there, but if it's not the right piece of equipment for the, what you're working on, it can make maintenance and make the crews a little bit more unhappy about going down there potentially. So we try to be very cognizant on the front end of just how these are installed where we can get in and maintain them.
Now, paired to the maintenance question, from a design perspective, the biggest element would be making it as easy as possible to replace the media if necessary. That would be by having your drain tile be below the treatment layer, if possible, if the site has enough grade to that to work.
Pre-treatment, also pre-treatment.
Dr. Gulliver, you had identified 5 days as a duration for inundation. What research or analysis went into that number, that duration?
That's a really good question. It's based upon research that we do in ponds and pond sediments. So I'm basically extrapolating from pond sediments to iron-enhanced sand filters. Pond sediments have a high sediment oxygen demand. Some of them have a really high sediment oxygen demand. And they can go anaerobic, low DO, in 2 days or less. But many of them take 5 days. So I don't think that we have an iron-enhanced sand filter that has that kind of sediment oxygen demand that pond sediments do, because they're just totally organic material. So that's where I came up with the 5 days. It's probably a conservative estimate, but we did find in our study, we ran into a site that had been inundated for almost a month and was releasing a lot of phosphate. They thought they had to basically to replace the media until we told them, no, just don't inundate it. and so it's not a problem. So that's where I came up with the 5 days. It's kind of a little bit nebulous.
One more in the audience, and then we'll go online.
Okay, I actually have two. So if you allow it, just to follow up on that, so I'm understanding that to be that water that is sitting there and it's kind of quiescently sitting there versus like new flowing water going through a system for a continual amount of time. Is that because it's about the dissolved oxygen? Is that?
It's all about the dissolved oxygen. Yeah, I'm flowing water through it. It probably would be okay, I think. You're assuming that the oxygen in the water, which is pretty minimal, is enough to supply the filter with oxygen. I'm not so sure about that. I haven't thought about that.
Sure, thanks. And then my other question is, when we're talking about replacing media, I'm just curious on panelists' experience in what that looks like, how you do it, how it gets done, what kind of equipment gets used, where you send it, stuff like that. If you have any, if you've gone through that yet.
We haven't done it yet.
We've done small repairs. Is large enough repair that we brought in a small excavator, and then we basically dig down to at least, well, we always think we're getting close to the drain tile, then we usually hit the drain tile, and then we break out the shovels. But yeah, for the most part, we've anything from a shovel to a small excavator, and then yeah, it's like we end up bringing. I would have to look to see where we brought the material. Our guys brought it to our shop first, and then that got hauled off, I believe, by Plastids back to their facility.
What happened to the media?
We replaced it. Like the media that came out of the maintenance area?
Yeah.
Yeah, it was small enough where we brought in new media just to replace what was in there. And it was a small enough cubic yardage where we brought in sand, and we brought in the iron, and then we mixed it with just basically using a skid steer. We didn't use the rototiller. So we feel that we got pretty good mixing there.
I'm wondering what happened to the old media.
We thought we hauled it off to Plastids. So we hauled it back to our shop, and then Plastids, we hired them to basically haul off a lot of our stuff.
I see.
So they took that and would have brought it back up to their probably Elk River location.
Do we have an online question?
Have you looked at the correlation between tree canopy cover in the watershed and the remaining phosphorus capture in the IESF? I'm assuming that means the remaining phosphorus in the water that needs to be removed, but maybe you have something to say about that.
No. There probably is a correlation, but that would take a lot of detailed analysis. Yeah, that would take a lot of detailed analysis, and we just didn't have the time or the funding to do that.
The closest thing I could think of that's been done would be as part of street sweeping research. So just looking at tree canopy over city-owned streets as an example, and then correlating that with the pounds of materials picked up, and that could be used to potentially figure out what's left after you've done your street sweeping to fine-tune loading onto a basin, but nothing marrying the two that I'm aware of.
No, it's, yeah, I just to add on to that a little bit, it's like, I know for us, we do a lot of street sweeping, again, kind of in the McCarran's area that has the William Street Pond. So it's like, we know how many pounds of leaf litter, sediment, and everything that we're pulling off the street. But yeah, it's like, we've never actually went through to look at what's coming off the streets. And we test most of it before we ship it out. So we should actually know what came off our streets. But we've never looked at basically rainfalls after that going through William Street. We might have enough data in there to try something. Be pretty crude if we're doing it at this point, but it'd be interesting to look to see how much is actually coming off.
Got a question in the audience?
Thank you. It's maybe mostly for Chris and Ryan, but I know MPCA has a database of all their iron enhanced sand filters. We've plugged our stuff in there. So there's quite a few around the metro, but so we're bringing our 7th one online in the Comfort Lake Forest Lake Watershed District. And we have a lot of questions on the O&M side and wondering if there would be interest in starting a sort of a O&M work group.
I'm all for it. Sure. You can even come down to Roseville. We'll walk through ours, cap regions, if you want to see how we maintain them or if there's questions about what's going on. Yeah, I think anytime we can, pass on the knowledge of what's already happening is obviously the most effective. It's easy to go out there and point to what works, what doesn't work, and if there's new practices coming on.
There is a work group actually started. Yeah.
We weren't invited.
I'm definitely not leading it, but there is a work group started, and I think Freshwater and I know Rice Creek has been involved, and I think there's if I'm remembering, some type of seminars that might be coming out this fall, or is it later? But there is one started.
Yeah, I think it's this fall, but we don't, I was just looking on my calendar to see if it was set, so we could maybe send it out to the group.
I can actually fill you in on that. Registration just opened up today, I believe. Where can they go to find that? Registration, the webpage. It just opened up today. There is a site visit being planned for the end of October, and then there will be a workshop in January, and then several more site visits after that. And yeah, that's a partnership between Freshwater, Capital Region, and the Water Resources Center.
It's even yours.
Yeah, so.
I didn't know about it.
Rice Creek, not Capital Region.
Okay.
Yeah, you're off the hook. So just watch for that. Maybe check Freshwater's website. Maybe we'll be able to put something up on Water Resources Center's website as well. Yeah.
Dr. Gulliver, you mentioned if we are growing plants on our iron enhanced sand filters that maybe they're not working as they should. We're pretty good at growing plants on our filters. Smart weed is taken over. What are the risks there? Is it just the added phosphorus load, or what are the other impacts from vegetation growing, and is it an absolute necessity to remove that all the time?
I don't think I answered your last question very well, so, and I don't think I'm going to do a very good job with this question, but yeah, plants and iron enhanced sand filters. The risk is that you're going to add the phosphate in the plant's organic material to the iron enhanced sand filter. So that's one risk, but that may not be the biggest risk. If you have a filter that has a lot of plants, a lot of different species of plants, it's probably not working that well. It's a sign that it's not working that well at removing phosphate. It may still remove particles, but it's not removing phosphate very well anymore because the plants are getting phosphate somehow. And so that's important. Now, with these little scrub plants that you see on every iron enhanced sand filter, tilling them in might be fine. Yeah, I don't think it would be a huge risk, but I think that if you have a filter that is full of plants, then that would be a problem because it's no longer removing phosphate.
I have a follow-up question, actually. Okay. So are the bound phosphate on the iron filings, are plants not able to take that up? Is it bound too tightly? Is it meant to be bound too tightly that plants' roots couldn't take it up like it could from normal sediment-bound phosphorus?
Yes, that was discovered in Andy Erickson's project. He could not grow plants in sand with iron. It didn't happen.
Yeah, try iron. Yeah. Ours does great.
I will mention if anyone's interested in that workshop, just come see me after today and I will hook you up with the registration link.
Not so much a question. I have two comments I want to add. One of them goes back a little ways, but I'll start with Forrest's question. If you're growing a lot of plants on there, that means it's not being maintained. If the sand and the iron will rust into a brick if it's not tilled and mixed up routinely, possibly even monthly. I mean, this can be a problem. So if you're growing that many plants, maintenance is an issue. Secondly, Bridget talked earlier about, I'm going back to your drain tile response. Tall cleanouts, yes. Vented cleanouts also. I've seen too many of these installed where the cleanouts are not vented. I've run into airlock situations where drain tiles can't drain if they're not vented. Obviously, that needs to be above your water line. Just wanted to throw that out there.
Anything online?
Can anyone elaborate on the sourcing and availability of iron media and any considerations for specifications relating to the material, mixing, and placement?
That's a great question. As a designer, we have to put specifications and all notes in plan sets. And so I guess the most recent sand filter we've done, it's always the contractor will submit the GP Connolly iron filings, because I think that's what everybody uses. Anybody use anything different? Nope, no other options. So that's what we spec. We say, here's what works, here's what the guidance is telling us to use. So great question, but that's what we always use, and that's the exact submittal we get from contractors. As far as speccing it, we say use the C33 sand, pretty much following the Minnesota Stormwater Manual guidance, and then trying to tell contractors exactly how to do stuff, is kind of challenging sometimes. So we do our best to specify the drain tile, specify everything that needs to go in it. So I don't know.
Pretty similar experience. We have an approved product list, which has one or approved equal. And as for means and methods, we require it to be well mixed, but tested in the field. So there's some room for contractors to use different means or methods, the skid steer method, rototill, or offsite mixing. So long as the field placement meets performance requirements, which is based on the Stormwater Manual, that's about the limits of how we specify things.
Yep, same for the city.
So we've got a lot of really great research coming out about iron-enhanced sand filters and their effectiveness and longevity. Are there any barriers that you encounter to taking those research findings and actually putting them into practice?
Part of it is just getting the knowledge out. So the report published in April had just the area ratios was very informative, but getting that information in an easily digestible way to public works staff and getting the general public's buy-in given the cost of these features is probably the biggest challenge. So there was an earlier question on stormwater treatment credits and how iron-enhanced sand filters might play into that with updates in research. The biggest barrier I'd see to getting it implemented in sites is having standardized tools and practices that designers can follow, that municipal staff can understand, and that, if needed, the general public can understand. And then there's always the aesthetic issue of having a bare sand site. The general public tends not to like bare sand. They wonder why plants aren't growing. But that's more of an education and outreach issue that can be solved with a simple chat.
I think some of the barriers come with all the site constraints that we find in designing. We have a blanket iron-enhanced sand filters treat this much, whatever percentage is, and tend to follow that. But there's no modeling software to say, oh, if you have 6% iron in your thing, this is what you're going to get. And not that we want to fine-tooth everything, but what kind of flexibility is there in the different sites because of all these different site constraints? So that would be maybe one thing I have to say.
I think I'd echo the same. Site constraints for existing sites. It would be great to be able to follow all of the guidelines to a T, but a lot of times it's just not possible. Elevation between overflow and like tile, and where your bench can be, how big you can make it, how big of a contributing area you have to this existing pond. You kind of do your best, and hopefully you'll catch, more dissolved phosphorus than you were, and make it worth it. But it's hard to follow all the guidance given that the site already exists.
Yeah, I kind of echo that. Just in regards to, again, we're doing a lot of retrofits. We're trying to put these in. We're trying to maximize all the areas. We try to follow the guidance as best we can. But yeah, just when we start looking at the infrastructure that we're retrofitting this into, we have to use professional judgment on, how this all works and how much treatment we think we're going to get out of it. But yeah, the research itself is very helpful on the municipal side, just because, it's like I can go to my leadership and say, this is why we want to do the project. This is, the benefits that we get from it. So it's like, the research is very helpful just in that regard to help for me just to even sell the project. And usually when I start talking about it to leadership and start referencing research reports by St. Anthony Falls, they usually say yes pretty quick. Just because, one, it's tried and tested. They do a lot of research and their reports are very thorough. So I don't get a lot of questions about, them wanting to read it and get through all of it. But no, it's like, that's one of the big things for us is just the research is very helpful because it moves a lot of this forward on the municipal side. It's like, we have permits with the MPCA. We have, we want to keep everything as clean as possible. So this is one very effective way for us to do that.
All right, go ahead, John.
Yeah, I have a couple things I'd like to say. First, there are those of us, maybe it's because it's the engineer in me, but I find bare sand filter to be beautiful. Especially if you put enough rocks in there that you kind of have, like the Japanese do. They have rock gardens, right, with sand in them and things like that.
We need to rebrand.
Why can't you do something like that? I'm sorry?
We need to rebrand.
That's right, we need to rebrand it. And so you could do something like that. That's like the first one that was done had a kind of a Stone Age look. The one out in, I've forgotten where it is, but it was still up my bar. But one thing I think that doesn't work very well and defeats the purpose of an iron-enhanced sand filter is to mix in compost so that you can grow plants. That has always been a failure because compost degrades. It's organic material. It degrades. What happens when it degrades? The phosphate that's in that compost comes out of the filter. And so it basically creates more of a situation than you think. And that's a part of another research study that Andy Erickson is heading up. We're looking for an alternative to compost in biofilters, not bioinfiltration. Bioinfiltration is where the water goes into the ground. The ground is a pretty good filter for most things except for nitrates and chloride. But otherwise, the ground will filter it out, including the phosphate, because there's so much iron down there and aluminum. But phosphate in a biofilter, where it goes back into the storm sewer, for that, compost really doesn't work very well. We have situations where you increase your phosphate concentration by a factor of 10 in a biofilter. So that's just an aside.
So that is actually all we have time for today. I do have one last question for each of our panelists. Maybe we could start with you, Paul. What are your key takeaways from today's seminar, and what lessons have you learned on this topic that you would like to share to the audience before we leave today?
The main takeaway from the seminar is that when selecting iron-enhanced sand filters as a potential BMP, it's very important to balance the ratio of inflow area versus filter area to get the desired design life and targeted TP removals. And sorry, what's the second half of the question again?
Any lessons that you've learned that you would just like to share before we leave today?
The importance of keeping in touch with SAFL staff and seeing what the latest and greatest research is coming in as we're putting in these BMPs, as this research develops, staying on top of it so that we can know what the expected design life of a BMP could be as we're optimizing our sites.
Thank you. And Bridget, any key takeaways from today or just anything about iron-enhanced sand filters in general?
I really enjoyed the time frame as well, like how to potentially figure out the life of your sand filter. That way, you can set expectations when a new one's going in, letting people know what it's going to take, how often it's going to be replaced. I think that was the big one, I think, for me, checking my notes. And just some of the maintenance, the filter fabric was interesting to hear about, the success of that. So probably implementing some of that after maybe some more discussions. So that's good. Thanks.
Great. Chris?
I thought it was really fascinating publication. There's a lot of really useful information in there for kind of taking a look at existing projects and seeing how do they compare within these equations. How long should we expect these things to last? And then I'm also interested in that the batch media test and being able to directly measure, going out and just sampling, how's this thing doing, and kind of getting something to compare that estimate with before we would go through the process of doing like a full replacement. I thought it was really interesting work.
It's similar to that. I'm most interested in just kind of the longevity of the BMPs that we have, and then using some of the equations, because I know, again, William Street is kind of our, first and foremost, and that's been in now for 14 years. So actually going back to look at kind of what the predicted lifespan would be on it versus what we have. We had the media tested a few years ago. I have to see if they gave us how much iron is left in and everything, but it would be interesting to see if we can look at that, or we can always do another test just to see where we are at and how it fits in with kind of the research that was done. Just because, again, Roseville is kind of its own little beast with just things aren't optimized in size. So these are put in, so it's interesting to see how much of an outlier we'll end up being. We'll be closer to probably the 15, maybe 20 year at this, because it was still operating pretty good a couple years ago when we had it tested. So that was kind of my big takeaway for the day.
John, 30 seconds.
Okay. I got a couple takeaways. One is that there's a lot of research to be done. A lot of things in this area, in stormwater treatment, stormwater analysis, And there's not that much work across the country and across the world being done, just because I think it's because it's too much down to the community. People at the federal level think this is a community problem. I don't know why the federal government does not fund research in stormwater. But there are lots of people who can do it. It's just that we have two things. We have the Local Road Research Board that gets money through MnDOT, and they believe actually that the water that runs off their roads and their parking lots should be, maybe they should look into what happens to that. Most there are MnDOT kind of, it's kind of MnDOT funding. Most DOTs do not believe that. Most DOTs think that that's someone else's problem, handling the water. And the other one is the Minnesota Stormwater Research Council. So we have two means of funding that other states just don't have. And that's why so much research is done here, but there's a lot to do. Thank you, Stormwater Research Council. They funded this research, they're funding us on other research, and we'll try and do our best for you.
All right, that concludes our Minnesota Stormwater Seminar Series event for this month. Make sure to check our website for a full schedule of upcoming seminars, and also check out our YouTube channel for recordings of all of our past seminars. Thank you for joining us today, both online and in person. And thank you to our panelists and our keynote speaker for co-creating this seminar with us today. I hope to see you all at future seminar series events. And in the meantime, please help me thank our panelists and our speaker.